So I was asked to do more of the same this week. So recall last week. What did we do last week? Last week we defined sheaves of modules and proved they were a category, right? I mean, we didn't. It wasn't a proof; it was a construction. But mathematicians call it a proof, and proved they were a category. We gave them the structure of a category on a sheaf of rings, right? On a sheaf of rings. So this week, let's make an example, and it's the affine case, right? So, construction of the sheaf of modules on Spec are associated to a module. Yeah, that's what we're going to do. And let's see how far we get. That goes there, right. So where do we start? I guess we import what we had last week. So that was import. Oh, so I should say that there's remark that there's a repo, right? There's a lean repository where I push stuff, and it's this repository here. Let me git remote -v. It's this thing here, and it's that. So there you go. So you can do something like lean project get that thing there. That, if I cut that and paste that, should get it there. And the material I'm writing is being piled into this repository. Okay, great. So we should start by importing the stuff we did last week. So what was that? Import, that should probably go up here. Import, I think it was sheaves of modules. Yeah, it was that. Sheaves of modules defs. Well, that's taking some time. So maybe I should... Let me just check that works. Lean ---- make src sheaves of modules. Have I screwed up? Oh no, we're fine. Sheaves of modules dot defs. Let me just compile what we did last week. Let me switch that off temporarily. It's just suddenly occurred to me that this might be... Okay, great, that's done. Okay, so now what's the idea? So we want to, so let R be a ring, and let M be an R module. So because we're using category theory language, in the old days we would do things like this, right? Variables R type, com ring R. But I don't think I want to do it like that. I think I want to do let R be a com ring. We don't have that. Okay, let me do com ring dot 0 there. So this says let R be a commutative ring, which is also a set, right? That's what the 0 means. Zero means it's a set, as opposed to a random class. Like Lena's got infinitely many universes, so I could choose a commutative ring in an arbitrary universe, which it's not the kind of thing that mathematicians want to do. And let M be a module. Let M be a module over R, which is also a set. So variable M module dot 0 R, I think that would be. Oh, and that hasn't worked. Okay, so let's import algebra dot category dot module. Is it there? Let's try that again. Oh, it is a thing. Great. I don't know. Module.abelian. That should be fine. There we go. And now, great. And so now, what do we want to do? So now the goal to make a sheaf of modules over Spec R. And there's two ways of doing this, right? As far as I know, it's sort of completely distinct, as far as I know, constructions. And the first one is I think this is probably in Stacks project. The idea would be if U is D of F is a basic open subset, then define M of U to be M1 over F there, and now use some sort of formal nonsense to extend to all open subsets. So that's one possibility, and the second possibility is the one in Hartshorne. Just define on all open sets at once, and the idea is that M of U would be the functions from U to the disjoint union of M localized at P, such that firstly A. Why am I doing it like this? I could make this whole thing into a comment, right? M is the functions from U to the disjoint union of P, such that firstly M is actually a dependent function, such that f of P is actually in M localized at P, and then secondly F is locally a fraction, right? I.e. for all P there exists some neighborhood V of P and elements, well, maybe some neighborhood V of P and elements, this will do, and elements sort of M in M and R in R, non-vanishing on V, such that f of P is such that f of Q is M over R for all Q in V. There. So that's how Hartshorne defines Hartshorne defines the structure sheaf on Spec R in this way. So those are our two possibilities. So historically, when it was me and a bunch of undergraduates defining schemes, we were following the Stacks project, because the Stacks project was just like free and online and open source. And so we went via definition 1, and definition 1 is slightly problematic because so the problem with definition 1, is that, oops, what have I done? The problem with 1 is that you can have U equals D of F equals D of G, but strictly speaking, and Lean is pretty strict about this sort of thing, M1 over F is not equal to M1 over G. So that's the problem. That's the problem with 1, and so 1 doesn't quite make sense. So this is what I should also say. What EGA does as well. 1 sort of doesn't quite make sense. And Grothendieck says, oh, it's okay because these things, they might not be equal, they're canonically isomorphic. But Loon is just like, but they're not equal. Like, so U equals U. You can't have a function. Yeah, M is not well defined, right? Because you're putting in two inputs that are equal, and you're getting two outputs that are only canonically isomorphic and not equal. So strictly speaking, it's not well defined. And so 2 is the definition we're going to go for. So we're going to go for 2. For 2 because there's no because it avoids canonical isomorphism nonsense, which is hard to make rigorous in Lean's type theory. I mean, maybe I should say another approach. So maybe I should give you sort of variant 1 primed. Maybe I should just tell you this: MB variant 1 primed. I define M of U is M1 over S where, so if U is a basic open, then you can define M of U to be M1 over S, where S is all the elements of R, which are non-zero, on U, non-vanishing on U, and this avoids the problem. So that would be another way of doing it, and that was the way we did it the first time we did schemes. So instead of just inverting, the issue is you invert F and you invert G and you get things which are canonically isomorphic. But if you just look at the set of all things which are non-vanishing on U, so F and G would both be in it. So it's M localized as a much bigger thing. But this is it's much more functorial. That's the point. It's much more functorial, and it involves fewer lies of the form. These things are canonically isomorphic, therefore they're equal. So that's what we're going to do. So that's going to be some work. So let's see how they do it. They do it for rings. So the question is, how do we make? So we should import algebraic. Do we have affine schemes? Check affine scheme. Is that a thing? That is not a thing. So we're going to have to import affine scheme. And oh, there seems to be a file called algebraic geometry affine scheme. Okay, great. So let's import algebraic geometry dot affine scheme. There we go. And now hopefully that will work. Oh, it doesn't work. Oh, because I'm in the I should open. Presumably it's called. Is it called? Yeah, it's called algebraic geometry dot affine scheme. So let's open algebraic geometry. There, and now it's worked. Great. Now let's have a look at the definition. Oh my goodness me. Oh, that's the category of affine schemes. Oh, so it's spec is what we need somehow. So spec is the functor from commutative rings to schemes. And now the question is, where does the locally ringed space come from? Oh, so what's a scheme? So I'm actually confused. The spectrum of I see. The spectrum of a commutative ring is a scheme. Great. Oh, spec obj. So there we go. We could use that instead. So this is the proof that this is the proof that it's locally. Oh, so the question is, where's the structure sheaf coming from? And it's this thing here, two locally ringed space. So let's have a look at that. So this is the construction of a locally ringed space attached to a commutative ring. And where is R? And so here's the sheaf. So sheafed space. So what's a sheafed space? This is a topological space equipped with a sheaf. Aha. So this is a topological space plus a sheaf of commutative rings. And the carrier, that's the topological space. Oh, okay, that's interesting. So this is the topological. So let's take that. That looks useful. There. And now let's go back to where was I? There. So that's how you make the topological space. And this is the pre-sheaf. So structure sheaf R. So here we go. Right. So here is how you put. So given R a commutative ring, here is how you put a sheaf of commutative rings on the topological space, which is the set of prime ideals of R. And you seem to use. So first you make a pre-sheaf of commutative rings. Aha. So this is what we should do, right? So that's how you make the pre-sheaf of commutative rings. So okay, so first we'll make. Let me just put these in comments everywhere. First we'll make a pre-sheaf of abelian groups. How about that? And that was, how did we do that? That looked like this. There. First we'll make a pre-sheaf of abelian groups. There. And then we'll make it, and then we'll beef it up. We'll beef it up into a sheaf of modules. That's the plan. Okay, and so how do we make a pre-sheaf of abelian groups? And so first they make the structure sheaf as a sheaf of types. So okay, so in fact I should be doing this. I'm going to reverse the order that I'm cutting and pasting these things, and then we'll beef it up to a sheaf of modules, and that will be like that. So the structure sheaf. First we'll make a pre-sheaf of abelian. First we'll make a pre-sheaf of types, right? So then we'll make a. Okay, great. So first we'll make a pre-sheaf of types, and the way we're going to do that is that, oh no, we won't. We're going to make a sheaf of types. Sorry. There. So first we'll make a sheaf of types, and then we'll make a pre-sheaf of abelian groups, and then we'll beef it up to a sheaf of modules. Okay, that looks like a plan. So how do we make the sheaf of types? And this is okay. So subsheaf to types is locally fraction. Oh, is there anyone that needs to be explained the mathematics? I should check with this before we start. Is everyone happy about this definition we're going to go for here? Has anyone got any questions about the mathematics before I launch into this? I'm going to take that as a no. And so the way the sheaf of modules works is that we're going to look at sections. You see, this is this says i.e. f is a dependent function, right? There. You know, f has got type pi p in u, m localized at p. There, that's exactly what dependent type theory can give you. Instead of writing a function from U to the disjoint union, we're going to write a term of that type there, which means the input is a prime ideal and the output is an element of the module localized at the prime ideal. And that will obviously be a sheaf, right? That's obviously a sheaf because there's no sort of local. That's obviously a sheaf. And now the issue is that then we're going to look at the sub pre-sheaf of things which are locally fractions, and the work will be to prove that this is a sub sheaf. And so that must be what's happening here. So what is locally fraction? So have we got? Did I copy that stuff yet? Yeah. So what's this is locally fraction? So okay. So then we'll make a sheaf of types. So what are we going to do first? We need to make. First we'll define. The sheaf. The sheaf of just functions, right? The sheaf of functions sending u to the set of f from u to the disjoint union of MP such that f of p is in MP, right? And then we'll define a predicate called is locally fraction. We may as well call it the same thing. Is locally fraction. Okay, so that's there. So that looks like the plan. So what is the definition of is locally fraction? So here we go. Golly. So that is the thing. So you see, what I'm doing is I'm cutting the stuff. I'm cutting the definitions that we use to make the structure sheaf, and I'm just going to mimic them. So we need the localizations of R. So what are the localizations of R? Where does this even start? Right, here we go. I think, wonderful. So this is a function. So this is what we need, I think. So I think we might finally be ready to we might finally be ready to actually do something. So where do we start? Here. Right, let's write some lean. The type family over prime spectrum are consisting of the localization of a module over each point. So these won't be commutative rings or local rings anymore. Let me just maybe I should just remove this for the time being. Have we got we've got a ring and a module, right? Yeah, we've got a ring and a module. So localization is P, and this would be type. I'm going to call it type because we're not going to do universes. And now I have to localize. Okay, so how to localize a module as a prime ideal. Jason, do you know how to do that?
Yes. So I think you need to import the file first.
Is it called localized module or something?
It's just called localized module.
And indeed I don't seem to have it imported. So I need to import algebra module localized module. Mute, your sound is horrible. Jason, can you mute? I'm going to mute you and then mute the sound. Jason! Mute yourself, this is horrible. I'm going to put... Oh, thank goodness for that. Right, I'm going to import algebra module localized module. And so, here it is, localized module, great. Let's go. Oh, this still doesn't work. Oh, because I've got a doc string. That could go there. Oh, why is it messing me around? Has that worked? Oh, we're about to see. Yes. Localized module, it wants a submonoid. Okay. It wants a submonoid. And how did we do it here? We weren't doing affine schemes. Oh, curses, I've lost all my stuff. Let's get back to... Yeah, spec obj. I've now got to go through everything again because I've forgotten where it was. Spec obj is there, and spec locally ring space obj is there, and sheaf space is there, and structure sheaf is there, and this is the... I don't want to lose this file, I don't think. Structure sheaf is the structure pre-sheafing com ring, which is... Got to wait for the orange bars to go away. I could just scroll up. Structure sheaf in type is locally fraction. Yeah, where's the definition of is locally fraction? Localizations, this will do. Localization at prime. So what's that? Localization at prime.
That is just an abbreviation of localization. Then you put in ideal dot prime comp, that thing. So
wonderful. Your audio is horrible. So what do? I do localized module p dot as ideal dot prime compl or something. Prime compl, and I need to mention m. What does localized module, how does this work? It wants a submonoid, which I think I've given it, and it wants a module, so great, m. There, great. And I don't want to derive com ring, but it would be nice if it was an add com group, I suppose. There. How about that? Does that work? Yes. Derive add com group. Okay, so that is the localizations, and now we need to now we need to define a predicate called is locally fraction. Okay, so let's have a look at is locally fraction. Can we go back? Go back. Go back. Is locally fraction. So what is fraction pre-local? So I think we need to make one of these. This is my guess as to what we do next. Predicate. We need. No, next we need to make is fraction. Great. Here we are. The predicate's saying that a dependent function, yada yada yada. Right. I need to steal this. That's the next thing. Then we'll define a predicate called is locally fraction. Let's do that now. So, this should be, I shouldn't be doing this in the root namespace, right? Let's go namespace module. That would be a place to put it, wouldn't it? Didn't like that. Command does not, I put it in the wrong place. There. Let's get rid of that. Right, the type family of a prime, yada yada yada. Now we're going to define, so this is the thing I just cut and paste. The predicate saying that a dependent function on an open U is realized as a fixed fraction. Let's do M over S in each of the stalks, which are localizations of a module, of a fixed module of various prime ideals. Def is fraction, and now opens. Why doesn't opens work? Presumably because it's topological space dot opens. So let's open topological space there, and now it says localizations. I see. This is the wrong localizations. So this is now m dot localizations x or something. Curses! What have I done? It needs a ring Rx. Yeah, that looks good. So this now says we've got U, an open subset of spec R, and we've got F, a function that takes an element of U to an element of the localization of of M at X. And this should be P. Why is this called X? P. Proposition, and that is that. And now we need to say that. First of all, we're saying this is globally a fraction. So there exists an M in the module and S in the ring, such that for all Q in the we could do P, such that for all P in the open sets, it's not true that S is in the ideal, and it is true that F of P. Now I have to think. And it is true that F of P multiplied by. Why didn't it like that? By fail to synthesize yada 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 yada. This is now. What is going on? What am I doing? Algebra map. So now, why doesn't this work? Algebra map. Because there's no R. What's this supposed to say? Let me think about the maths. What maths do I want to say here? I want to say I want to say that F of P. What do I want to say? I want to say that F of P multiplied by. So I want to say S multiplied by F of P equals M. That's the idea, right? So that says, how do I get S? This is S is in R, and is this? What is this a module for? There's an interesting question. Is M dot localizations? Let me do a little test. Section test. end test. Let's have variables. Let's have p in the prime spectrum dot top r, and let's have r in r, and let's have m in m dot localizations rp. That's a shame. Why does that not make sense? I just defined what? Oh, I misspelled it. Got it. And now, can I give him an element of m dot localizations? Rp colon is bub m. That's what I was going to put. Oh, wait. Example. Right. So, Jason, you didn't make localizations RMP. Oh no, it might be my fault. Is this a module R? Oh, can you do that? Maybe I can't do that. Instance. What do I want this to be? I probably want this to be a module for the localizations, right? Maybe I'll do module localization p dot as ideal. Is there no abbreviation for this? Prime compl. And now localizations p m dot localizations p. What about that? Oh, it still doesn't like this. Colon equals sorry. Oh, it doesn't know what p is. Variable p. Oh, let's have it here. So if p is a prime ideal, then is this localized module? Oh, what have I done? That's the ring. M dot localizations p. Oh, M dot localizations RP. Is it that? Great. Colon equals, and now the question is, will infer instance work? And it doesn't work, unsurprisingly. So begin end. So we probably have to unfold localizations, right? Oh, unfold module dot localizations. What? Let's delta it. Well, that's worked. There, and now now is this true? Apply instance. Yeah, that works. So I can derive adcom group, but can I also derive module, this thing here? There. You see, every time you make a new definition, it adds a new layer of obfuscation. Oh, curses. Oh no, I don't know P yet. I'm not sure I can do that. Okay, so I'm going to have to... What was this called? Show term. Let's just cheat. It's called that. So it should be localized module is module. Okay, great. So now I've made a new definition called localizations, and now if I evaluate, yeah, so this is, it's just the localization, rather annoyingly, but the idea is that P is an input. And now the localization of M at P is now a module for the localization of R at P. This is, oh, do we even have? Wait, I could do localizations. Wait. Localizations. Are there two of these things? Oh man, that's module localizations. But is there a root one? Isn't that somehow what they were just? No. Did I not? What's the difference? Is that not imported? I thought we just saw that. What's this? Oh, algebraic geometry structure sheaf localizations. Huh. Okay. Did we open algebraic geometry? I think we did. We could make this a module for structure sheaf dot localizations. Doesn't like that. And now it just wants. And now we just want P. Oh. What have I done wrong? Oh, it wants R first. Oh, great. There we go. So now we've just defined a new thing called module.localizations, and it's the localization of the module at the complement of the prime ideal, and we've just given it the structure of the localization of the localized ring. And so now we want to define a predicate called is locally fraction. So now that we don't need that test anymore. And that was we were in the middle of this, weren't we? So now we have to do s dot right. Got it. So now we want to write s times f of p is equal to m, and s is in R, and so now we need some kind of can I just coerce this? I wonder if there's a coercion. So I want to consider s as an element of that set, right? And s as an element of that set equals 0. It doesn't like it, but if I put a little up arrow, does it like it? Oh, now it likes it. Great. So this thing here, but I don't want it to be equal to 0. I want to dot it, I want to bob it with f of p, and that should equal m. And so it's up arrow m. Is that going to work? Oh, Jason!
I think you need to use localization, localized module dot merge m1.
You didn't do a coercion? Localized module dot mook m1. Okay, alright. Okay. So that's what it means. That's what it means for a section. Yeah, we call these function, right? This is a this is a dependent function f. This takes a prime ideal in U and sends it to an element of the localization of m at that prime ideal. And what we've just defined is a predicate on such functions, saying I'm a fraction, which means there exists some element of m, such that I can. There's some element of m and some element of r. So m over s, such that this is locally. So this is equal to m over s on the entire U. So that's what is fraction means. And now that can go. And now this is the next thing.
I think if you write this, you might as well just write after equals localized module dot merge ms.
Sorry, what should I write?
So you might just want to write down fp equals m divided by s. Maybe that's just easier.
Oh. Because I can. You're saying I can put s here. Yeah. Okay.
You can put s here, but you have to change the first as noting something into an existing statement because you have to use a hypothesis later.
Yeah. So we want s to be an element. So this is pointy bracket s comma something. Yeah, we want this. So there exists an m and an s. And a hypothesis there, and a hypothesis HS that S is in the complement. Oh, why is that not working? Prime, that was working before. Oh, we haven't got a P. I see, for all P. For all P in U. For all P of type U, S is in this. What did I do? I broke it. What did it say before it worked? There. For all P of type U, S is in. Oh, this still doesn't work. Maybe I should get rid of that.
Computation is wrong. You have to introduce P first, then the hypothesis HS.
I have to introduce P first.
Yeah, you have to introduce P first, then they introduce the HS hypothesis. So something like I just type in the chat.
Oh, there's chat, is there? I'm really sorry, I can't read the chat. There's the... Thanks. There exists an M and an S such that for all x... Oh, you think? Yeah, okay. There exists an M and an S such that... Aha, I see. For all P... For all P... yeah, I think this might be a good idea. For all P in U... for all P in U... Firstly, there exists a proof... HS... which says that not... Well, there's H... There's... It says this, right? Such that for all P in U... There's a proof that... There. I'm slightly annoyed that it's still not working. Such that, sorry. Why doesn't this work? Let's have a look at the errors. Don't know how to synthesize placeholder. Oh, have I screwed up? Prime dot spectrum as ideal. P. Maybe I should put P dot... Oops. P colon prime spectrum R. Would that be happier now? Oh, what is going on? This worked before. Why is there no coercion? Is it P dot? Oh, is it P dot 1 or something? Yeah, P dot 1. Ugh. Oh, is it up arrow? What about that up arrow? No, that doesn't work. P dot 1. Okay. Oh my goodness me. This says there exists an M and an S such that for all P, there is a proof that S is not 0 at P. This just says S is... this could say S is not in P, right? There exists a proof that X is not in P. And... the proof that X is not in P such that... This should now be okay, do you think? Such that F of P equals... localize module dot mc ms this thing here, there, shs, and that has actually compiled. I do have an error. What's my error? Oh, it's my error that I didn't put end module or something. Yeah, great. Okay, no errors. Wonderful. So that's what it means to be a fraction, and now we want to do locally a fraction. Is locally fraction. This is now going to be a local predicate on m dot localizations are... Oh, never heard of local predicate. Where does that live? Oh, it's in top. So let's open top. And now is... Oh, we haven't got an is fraction pre-local. What's that? Check is fraction pre-local. Have I got that? I was trying to copy everything. I haven't got is fraction pre-local. Check is fraction pre-local. Is that a thing? There it is. So what does that say? That says this. There, that's what we need to prove here. Let's have a look. The predicate is fraction is pre-local in the sense that if it holds on U, it holds on any subset of U. Okay, is fraction pre-local predicate. And, so I need to open top earlier. So the claim is that, and now, yeah, this is wrong because this is now m dot localizations are or something. M, what's the type of M? M's got type module R, so we shouldn't actually have to, keep putting in this R, right? Where's the definition of localizations? I want to do, this is a bad... What about if I do this? Does that still compile? I've broken something. Yeah, now I might have to. There you go. Oh, that's better. Oh no, something's still broken. What's broken? Line 84. Yeah. We can get rid of the R's. We don't need the R's. And now what else is broken? 907. M dot localizations. We're going to get rid of it. Great. And so now the predicate is lambda u f, and now this is this. What's the problem here? Is it moduled it, so m dot is fraction f. Oh, that's cool. That was going to be our first proof. but the proof managed to randomly work anyway. So what did we just do? What was the theorem we had to prove? Let's actually have a look. The theorem that we just accidentally proved is that if U is a subset of V and F is a section defined on all of V and F is a fraction on V, then F is a fraction on U. Okay, yeah, that doesn't sound too difficult. Okay, so that was supposed to be our first proof, I guess, but we've got it for free. And so now we're going to claim that being locally a fraction is a local predicate. So local predicate is fraction pre-local. This is m dot is fraction pre-local. Get rid of that. That's a shame. And it doesn't work. And it's expecting it doesn't want the R, of course. There we go. Oh, great. So wonderful. So we've got that for free as well. Given a pre-local predicate, we can always construct a local predicate by asking I see. So now we've got a new definition. So this says a dependent section f which maps U. So I'm going to use this dependent function notation. So this is a function. The weird thing about these functions, right, is that they don't go from a domain to a codomain. They go from a domain to, they're like sections. They're like sections of a vector bundle. They take the point in the domain to a fiber above that point, right? So it's M localized at P. A dependent section, so this is a doc string there. A dependent section is locally a fraction if U has an open cover consisting of, so if U has an open cover such that the restriction of F to the cover is a fraction, M over S. There we go, and we've got that. And now, okay, great. So now apparently we're ready to make a sheaf of types. The structure sheaf, valued in type, is the subsheaf consisting of functions satisfying locally fraction. So let's see if we can pull that off. So not yet AB, because we're going to make it a sheaf of abelian groups. So this is not the structure sheaf either. The sheaf of modules, associated to M is the subsheaf consisting of functions. Yes, so that's right. So then we'll make a sheaf of types. Comment that out there. And now what? Structure sheaf in type. So it's not structure sheaf, it's module sheaf in type, and it's going to be a sheaf of types on the topological space, and it's subsheaf to types, and it's M dot is locally fraction. There we go, great. So now we have a sheaf. Now we have a sheaf of sets on the topological space, and it's and it's the things which are locally fractions. Then we'll make a pre-sheaf of abelian groups. Okay, that's the next thing to do. So this is structure pre-sheaf. So it's not a structure pre-sheaf. It's just a pre-sheaf in AB, because it's not a sheaf of rings either. It's a sheaf of abelian groups. So this would be a pre-sheaf of abelian groups on the prime spectrum, and the objects would be we have sheaf in type, right? Yeah, so this should be M dot sheaf in type, and then we don't have to mention R. and now we're supposed to make it a commutative ring. Sorry, an abelian group. So that hasn't worked. Oh. It hasn't worked because ab of isn't a thing. Add com group dot of. Oh, that isn't a thing either. Oh, that's a blow. Oh, wait, no, it is a thing. Add com group of is a thing. Oh, I see. It's just complaining that it doesn't know why. Yeah, okay, so we need to prove something. Was that... Did I miss that? Yeah. So here we go. So we need to prove... Aha. So, oh, golly, this is long. Right. So the next step... So the next step is then we'll show that each of these types is an abelian group. And we're going to show it by showing it's a subgroup of an abelian group. So this is, let me copy it. Def. Why is it a def, not an instance? Def. Huh. Oh, I see. They make it. Right. Okay, so this is what we're going to be inspired by now. There, but our proof is going to be easier because we only have to prove. There, let's have a look. The function satisfying is locally fraction form a subgroup. There. Sections subgroup. And this is going to be an add com subgroup of, and this is m dot localizations x. Oh. Doesn't like that. Oh, is it because I haven't opened opposite. Open opposite. And it doesn't like add com subgroup. Oh, is that not a thing? What? Is it add subgroup? It's add subgroup. And I don't want to call it X. I want to call it P. And the carrier is... So I'm trying to make these... I'm trying to make the subset of the sections which are locally fractions. So this is m dot is locally fraction dot pred f. That looks fine. And now what's it complaining about? That proof is broken. That proof isn't necessary because 1 isn't an element. That proof... Well, every proof is broken. Neg mem we'll need to do. Mul mem we don't need to do. There, so we could do that. And then we can get rid of that. Right, so this is the proof we need to fix up. So 0 mem, okay. So what do we need to prove here? We need to prove that 0 is locally a fraction. That's the point. So how did the first line go? The first line has gone really well. So let's actually try and work out. So how are we going to prove that 0 is locally a fraction? We're going to let... Am I back? That was exciting. I lost
Yeah,
internet.
you're back.
Wonderful. So how are we going to prove that 0 is locally a fraction? We're going to choose... We're going to... Why are they... the idea is that 0 is going to be locally a fraction because it's 0 over 1. That's the idea. And now to prove that that works, we are going to have to prove that 1 is not... we're going to have to prove that 1 is not... No, 1 is in the complement of an arbitrary prime ideal. So this rewrite has failed. Aha, so what's this prime compel? Prime compel is the compel. So can I change... Is the issue that change 1 not in something? Does that work? Hard luck. 1 is not in this thing here. How about that? You like that? What? That's a bit annoying. Oh, that has worked. Intro. We can intro H. And now... Oh, man, why can't... What? This is exactly... So what's happening here is that this assertion here, 1 is in the complement of this prime ideal, is definitionally equal. Why can't I get it to work? 1 is in the complement of this prime ideal. Copy. Surely that's definitionally equal to 1 is not in that thing there. Why doesn't it like that? Oh, it's the wrong one. Oh, this is going to work. It's going to work. It's going to work. There we go. I got the proof working again. So 1 is not in that prime ideal, and now 1 is not in an ideal if and only if the ideal is not the whole thing, and a prime ideal isn't allowed to be the whole thing. Okay, great. So there's the proof that 0 is in. So you see, I'm cheating. I'm not writing the proofs. I'm just like... instead of writing the proofs, I am sort of modifying the proofs of the structure sheaf. So now what's going on here? We've got to try and prove... let's do negmem first. Negmem is going to be easier than admem, right? Let's steal negmem. There. Let's get negmem working. So this says intros A, H, A, X. So A is the function. So A is a section. HA is the hypothesis. Am I still here? The fuck? Hi. Hi, nice to see you all. Can you hear me?
Hello.
Hello. Teams just decided to log me out. So I had to type in my password again. Anyway, I was about to try and prove negmem. I don't know when I got logged out because I did. Oh, am I not sharing my screen now? Let's share that. Right, I'm going to prove negmem. So, what's terrible notation? So A is the function, A is the section that takes a prime ideal to some localization. HA is the hypothesis that it's locally a fraction. X Okay, and now I've got to. The point is, I've now got to prove that minus a. I'm trying to prove that these being locally a fraction is a subgroup, right? Because I need a group structure on it. Because I need to make the sections into an additive commutative group, and so then I can make them into an R module later. And so the easiest way to prove that they're a group is to prove that they're a subgroup of the group of sections. And so I've got to prove that if A is locally a fraction, then minus A is locally a fraction. So I've got to prove that if X is a random point, then there's some neighbourhood such that minus A is a fraction. And what we know is that A is locally a fraction, so A will have so X will have a neighbourhood where A is a fraction, and that's presumably this line. Yeah, so X has got a neighbourhood V with the property that let's call this R. I don't want to call this R. It's in M. Let's change R to M. There. Oh, and it doesn't like it. What have I done? And W is the hypothesis that for all P. Right, W is the hypothesis that you are globally a fraction on V. And V is a subset of U. Great. So we want to refine V. Oh, we've got two. Oh dear. What's this M? Oh, this should be HX, right? Is this HX? Does that work? Oh, that's worked. I could call this HXV. That might be a better name for it. X is in V. There we go. And so now, of course, the idea is if A is globally a fraction on V, then negative A is also globally a fraction. So now the claim is that some goal is true. What's the claim? So now we let Y be a random element of V, and then we use W. Our case is WY with NM. With NM and W, that NM has got a lousy name. And now we have to prove exactly. I mean, let me call this should be called HS, right? HS is the hypothesis that S is not in the prime, and W says we could desimp at W probably. Desimp only at W. W looks a bit ugly to me. There. Oh, it's now called W1. Rotten luck. W1 says that A of Y is M over S. And so now we've got to prove. So we can just do refine. We can just do use whatever it was called, HS. Right, great. And so now does this proof work? No, it doesn't. Does that do? I mean, let's just comment this proof out for a while. I'm sort of following my nose, right? The idea is I'm trying to prove that if A is locally a fraction, then minus A is locally a fraction. And the proof is if A is a fraction on V, then minus A is also a fraction on V. So now what does this say? Desimp only. We've got to prove that minus A of IY is... So there we go. We've got to deduce this from W1, right? I wonder why... Can I do that now? And will it be? Why is it? I wonder why they call it. I wonder why they won't. I wonder why W is somehow stuck. Anyway, not that it matters. So W1 is the hypothesis that A of Y is M over S, and now we've got to prove that minus A of Y is minus M over S. Okay. So what happens if I simplify it? Oh, that's handy. So what about if I simp with W underscore 1? Then there we go. Great. So now I've got to prove some fact about localized module MOOC. And I'm tempted to ask Jason.
It's called localized module. dot merc or merc, one of that.
Apply localized. Did you write this API?
Yeah.
Neg.
3 months ago, something like that.
Bingo. Yeah, got it. So there we go. I think our proof is nicer than their proof. I shouldn't really do. I should really do this, right? And do I need these? Apparently I do. Oh, but let's just. Let me just. Did that work? No, it won't do it. Huh. Oh well. This proof stinks, right? Because I shouldn't be using w_1. But anyway, it compiles. Let's just press on. This stinks. Oh, can I do? Oh, I don't know how to do it. This is really annoying. Why does? Why will Lee not clear W? Oh, I've got 2 W's. Oh, I've got 2 W's. Since how long have I had 2 W's? Why is this called W? This is a hypothesis. Oh. This is a hypothesis about M. Why don't I call this HM? There, and then our case is HMY with HS, and now, aha, great. And now if I simply hit W, hey, it's still called W, excellent, okay. Yeah, it was my fault. I should be writing the proof properly. Dsip only at W and there. Super. And now finally, boss level. I've got to prove that the sum of 2 things which are locally fractions are locally fractions. So let's go. What am I doing here? We've got A and B are sections. HA says A is locally a fraction. And HB says that B is locally a fraction. And now I've got to prove that A plus B is locally a fraction. So I've got to prove that given a prime ideal X, there is a neighbourhood that actually makes it a fraction. And how are we going to do this? We're going to say, well, A is locally a fraction. So is this good? VA, that's good. MA is not a great piece of notation. IA, RA, SA, and WA. Can I live with that notation? I don't really like... Oh, does this proof compile? No. If it compiles, I'm happy. Okay, let's go with stinky notation. So now the idea is that A is a fraction on the open set VA and B is a fraction on the open set VB, and so A plus B will be a fraction on VA intersect VB. And did that line compile? It did not compile. So yada yada yada, let's put an underscore there. And now let's, oops. So that has compiled, and now I've got to prove that I've got to So is this like use 37? Is that? No. What's? I don't know what my goal is now. Will that tidy it up? No. Yeah, no, not really. I don't know what the goal is. But it's certainly not... I don't know what this means. Let's have a look. What is... How do I prove that something is a... How do I prove... Oh, I see. I've got to... I've got to... I've got to do refine we're going to refine underscore, comma, underscore. That's the, so I could split, that's the thing to do. So what have I got to do? I've got to give an element of M. That's why use 37 didn't work. So use RB, will that work? Use RB. Okay, great, that works. I see. So what the goal now is to give element of M, which is presumably the numerator. Have I got to give the numerator and then the denominator? Yeah, I've got to give the to give numerator and denominator. Okay, that's what we're doing. So we're going to use, I mean, this doesn't work. This is a shame. So why doesn't this work? So RA is in M and SB is in R. Oh, I see. So this is probably, it's probably use SB small, because SB is in the ring, bub RA plus SA bub RB. And that didn't work because I spelt it wrong. And that did work, great. So in fact we could have kept going here. We can do this. We can do that, and we can still do SA times SB now, because that's going to be the denominator underscore. Does that work? Yes. There. And now intro y, yada yada yada. So now what are we doing now? So now we're trying to prove. Now we're trying to prove something. And now I've got two WBs. Was that expected? Yeah, that's rubbish. Let's call it WA primed and WB primed. So now we've got to prove. So first thing is we've got to prove that the denominator for A and the denominator of B are not in the prime ideal, and that's because NMA says the denominator of A is not in the prime ideal, and NMB says the denominator of B is not in the prime ideal. I don't have to prove that because that proof works. That's handy. So that proof still works, and now this is the problem. So let's comment this out and have a look. Because we somehow changed the definition. So now what have we got to prove now? We've got to prove, let's desimp only, see if we can make some sense of it. We've got to prove that A plus B evaluated at, so A plus B is a section, and then we evaluated at the prime ideal Y, and it's equal to this mess here. So, and how are we going to do that? The idea is that we know. So we could desim only at WA prime to WB prime down the goal. Let's see what that does for us. So WA prime says that A of Y is R over S, RA over SA, and WB prime says that B of Y is RB over SB. And so there is a chance that this is REFL, right? Curses. That's annoying. So what's the, wait, can we make this REFL? What's the definition? Let's try congra primed. Congra primed is REFL, except tell me what didn't work. Oh, what? Oh, this must be really close to being REFL. A plus B evaluated at Y is... Oh, no, it's not REFL because I haven't used... Yeah, I need to use... It's not REFL at all because I need to use WA primed and WB primed. A plus B localized at Y. Is that surely that is just change A something plus B something equals something. Yes. It's A of Y plus B of Y. And now, and so now we can probably rewrite. Can we rewrite WA primed? No. Can we rewrite WB primed? No. That's a shame. Why can't we rewrite them? That says A of Y plus B of Y is the thing that we know it is. And oh, is the problem? Yeah, these are sort of not quite the same, are they? A of, can I change this? Let's see if we can do this. Change that. Do you like that? What? Do you like that? What? Come on, like me. You like me. Great. So, yeah, the issue was some syntactic equality. So now we should be able to rewrite WA primed. Rewrite WA primed. Great. And now it would be really nice to rewrite WB prime, but the thing is, did they have to deal with this issue? And apparently they didn't. We want to. The problem is that this is B. The thing about Y is it's in VA intersect VB, and this is a proof. This says Y is in VA intersect VB, and therefore it's in V. Yeah, I need to some diagram commutes. I bet change doesn't do this. I bet this won't work. So this is the thing that that's what we want it to be. Let's copy that. But I bet this won't work. Expecting failure. Oh, it worked! Oh, that's handy. So I can rewrite WA primed and WB primed. There. And now I'm hoping that this is just going to be a statement. Now I'm hoping this is the definition of addition. And it is. There you go. So we have proved. What have we proved? Oh, I want to comment out like what's noise on line 65. We can get rid of that. And we have an error. We have errors. Where are the errors? So now we know that this is a subgroup, and so now what do? We're going to cheat. So what did we just do? It wasn't that. Wasn't that at all. What did we just do? I was just copying from something, right? Wasn't any of those. I just copied this proof from something. Oh, let's search for this. Where was I just copying? It was structure sheaf, of course. There, we've just done that. They proved it was a subring, we proved it was a subgroup, and now we have to do there. Now this is the next thing. And now we need to prove it is a... so now it's a subgroup, so now we need to prove it's a group. So this is instance add com group sheaf in type obj. And we've got u, and I'm claiming that this is an add com group there, and this is this thing here. This is a subgroup of this thing here. What? This is m.sheaf in type. M.sheaf in type, and I can remove r. That is now compiling, and the proof is now sections subgroup. M.sections subgroup, and now remove the r. U, and it's to add com group. If that's a thing, is that a thing? Apparently that's a thing. Great. So now all of a sudden these sections are a group, and so now some of this might work. The structure sheaf valued, not the structure sheaf. The pre-sheaf valued in ab, constructed by dressing up the type valued pre-sheaf associated to an R module. There. And it's thinking really hard. Why is it thinking really hard? Oh, well, this is nonsense. So m.sheaf in type there. Will that make it any better? Oh, at least now it's compiled. So it's complaining that we shouldn't be proving map 1. It's complaining we shouldn't be proving map mul. There. And now it's having a good think and it's compiled. Great. So we've made a pre-sheaf of abelian groups. And was that... Where did I just find that? Oh, it was in here, wasn't it? That was the sheaf of types. That's the pre-sheaf of common ring. That's where we've got before. And are we going to prove this? Might be useful. Let's prove this just in case it turns out to be useful. Structure pre-sheaf. This is pre-sheaf conf forget. M dot pre-sheaf dot pre-sheaf in com ring, and then we'll forget ab. No, m dot pre-sheaf in ab. Did I call it in ab? Yes. Compose with forget ab, unknown identifier. So what do I forget? Oh, it's category theory dot forget. Let's try that. Let's open category theory. Let's see what it thinks of that. Oh, it still doesn't like forget. I don't think it's any of those forgets. Is category theory forget not a thing? Check category theory dot forget. Oh, dot exact functor forget, is that what I want? Let's go back to let's see which forget they were using. We can dump a lot of this stuff, right? Derivation. Which forget is this? It's category theory dot forget. So it's absolutely category theory dot forget. I think I just closed the file I was editing. This is category theory dot forget. So why is unknown identifier? Open category theory. Why does it not let me do that? Have I not got it imported? Wait, category theory dot forget definitely exists. Unknown identifier forget. Category theory, I give up. Category theory dot forget. Bingo, works fine. No idea why that was failing. Is isomorphic to m.sheaf in type. There. 1, and this is nat.iso unknown identifier. Nat.iso is where? Category theory. So I should open category theory. Open category theory. And it still doesn't like it. What am I doing wrong? Oh, is it because I'm in a namespace? Oh, it's because I'm in the... Let me open it outside the namespace. Where do I go into the module namespace? Yeah, let's do it here. Now it's going to work. I think there's a namespace called module.category theory that somebody made by accident. So there you go. So this proof works as well. Great. And now, what are we doing? 5:30. Great. Structure sheaf. Yeah. The structure sheaf valued in com ring. Yeah. So this is what we need to steal. There. This is now going to be a sheaf of abelian groups. Boom. Def spec dot. It's fine. Def sheaf ab prime spectrum HR equals m dot pre-sheaf in com ring. There. Pre-sheaf in ab. It's never heard of if sheaf if is sheaf comp. I don't even know what this is. What is sheaf if is sheaf comp? Is that a thing? Top dot pre-sheaf. Oh, so I need to open top dot pre-sheaf apparently. Open top dot pre-sheaf. Great. And then is sheaf and this is structure pre-sheaf comp. So that was pre-sheaf comp forget. This is m dot pre-sheaf comp forget, and we'll forget r as well. And now what's the problem? What is the problem? Oh, this is totally wrong. This is m dot sheaf in type. That's definitely a problem. Oh, that was the only problem. Great. So I've completely stolen the proof that the structure sheaf is a sheaf of rings, and I've made a proof that this is a sheaf of abelian groups. Wonderful. And then we'll beef it up into a sheaf of modules. I suppose we should. So we don't need that anymore. Oh, that was it. So we could beef it up into a sheaf of modules, or we could... I suppose that's what we should do. Okay, so def sheaf of modules. And I call that was when I was doing capital letters last week, right? Sheaf of modules. And now I need the ring space. And the ring space is I've got this written down somewhere, hang on. It is right. So the question is I think it might be this. No, it's not that. Oh, I'm looking at the wrong thing. Oh, here we go. It's apparently... Oh, what a bore. So I need to... So the problem is I need a ringed space, right? I've got R is a ring, but now I need a ringed space, and so I should probably go back to check the definition of scheme. So how do I make a ringed? So a scheme is a locally ringed space. There we go. So we could use that. That looks like the locally ringed space attached to a commutative ring. So we could do this. But now it's going to complain, yeah, this is a locally ringed space and it wants a ring space. So let's try 2 ring space or something. Is that a thing? Oh, come on. So given a locally ringed space, the question that's left is, given a locally ringed space, how do I make a ringed space? So let's have a look at what a locally ringed, what is a locally ringed space? How how do you make a ring? Ah, here we go. It is to sheaf space. That's what it's called apparently for some reason. To sheaf space. Ah, that's worked. Wonderful. Colon equals underscore generate a skeleton, and the abelian sheaf is hopefully going to be m.sheaf. And that has worked. And the module structure is, let's just check everything's there, and then the compatibility bit is sorry. Right, that looks great. And now the module structure, we need to, I don't know what we need to do. So for every open set U, this abelian group, we need to make it a module over a ring. So let's generate the skeleton. Where's the data? There it is, it's smul. So smul is the data. So how am I going to, so there needs some, yeah, we're going to need some, we need something extra, don't we? We need an action, of the sheaf of rings, m.sheaf.val.obj. What is m.sheaf.val.obj? Is that, that's probably m.presheaf in ab. So let me begin end. I just want to experiment. So intro x, and then dsim only at x. What the heck is x? X is a prime ideal. So let's put intro p. Dsim only at p. X is a prime ideal contained in U, and I now need to define a linear map from M of U to M of U. And m.sheaf.val.obj, what exactly is that? Let's delta m.sheaf, module.sheaf. And let's desimp again. So this is m.sheaf in type. Oh, so okay, so I've gone too far. So let's just make it m.presheaf in ab. So I think we need to probably need to make some action before we embark on this. We could maybe do it. Where are we going to do it? I suppose we could define an action of the ring on the sections, like the possibly discontinuous sections. Oh, dear. We could maybe make... Maybe we should make this thing here into a module. Would that work? So how about let's do def sections module. Do I want to do this? Sections module. Let's go. Let's do it. Let's make it module. Oh, so I need U. I need U and open set. I don't think I need to do anything opposite. Sections module. So U is an open set, and what I want to make is a module structure for the ring. So structure sheaf. Should we use structure pre-sheaf in com ring R? That might be a... Is that the thing to use, I wonder? Because we need it to be a ring. Okay, let's... Structure pre-sheaf in com ring. I suppose we could just use that. No, let's do it. Structure pre... Let's do it this way. Module Did I cut it? No. Structure pre-sheaf in comring. Structure pre-sheaf in comring, and I need to give an R there, and now that is a pre-sheaf, and so I can think of it, a pre-sheaf is defined to be a functor, and so the functor evaluated on the objects are, now I think that might be a ring. There, now what's it complaining? Oh, sorry, U. Oh, doesn't like it. Oh, wants U to be in the op. Oh, hard luck. Okay, so we are going to make it an op. This has to be a module for that ring there, and so it's going to be pre-sheaf, put it in brackets, pre-sheaf in ab. Is that a thing? I thought I made pre-sheaf in ab. I just made pre-sheaf in ab. Sheaf in type. Oh, I haven't made it yet. Oh, no. I'm talking nonsense. I want to make the whole thing. This thing here. Let's make the whole ring there. Oh, and then we have to open opposite slightly earlier. There. Let's make that into a module. Colon equals underscore. Great. And now the smul. So, lambda p, comma, underscore. What am I? Lambda p. Oh, no. Lambda, that is an f, and that is an m. And now I need to make an element of the module, so let's let P be a prime ideal. And I simply want to do the multiplication is MP, is fp.mp, right? So it's fp, is that a thing? Bub mp. And it doesn't like fp. Maybe, can I do f.1, is that a thing? It does like that. Okay. So there is the definition of the module structure. Okay, so the ring is the continuous sections, and the module is the possibly discontinuous sections. And is there something called a submodule? There's definitely a submodule, right? Yeah, great. So now we have to check lots of axioms that should hopefully all be easy. So let's sorry them for the time being, because I need to start thinking about wrapping up. There. And now I want to prove that this is a submodule. Can I put submodule? Oh, I need to give the ring. And the ring is this ring here, I guess. The ring is that thing there. Boom. Oh, what? Oh, because I didn't make it an instance or something. Let's make it an instance. And now it works, great. And now what's it complaining? So we're missing some axioms now. So we want smul mem primed. Oh, we're not supposed to have proved neg mem. Oh, we were wasting our time. We don't need neg mem. But we do need smul mem primed. So what's that? Smul mem primed. Colon equals begin. Sorry, end. How it hates it. Unknown identity. Oh, was it called smul mem without the primed? No. Smul mem primed. I've done something stupid. I've written it end. There we go. That is the stupid thing that I've done. that now compiles. Great. So, no, but this doesn't compile. What have I done here? Section submodule. Invalid definition. Apparently I've already made... Did I make that? I didn't make it. What the heck is module.section submodule then? Check module.sections submodule. Is this me? No, there is a thing called module.section submodule. The flat sections of a function into module.
Instance you just made.
Sorry?
It's the instance you just made. It's called section submodule. Is it not?
Yeah, so I'll need to call this section submodule prime. And now this is sections submodule module primed u, and now to module. Is that a thing? How do I make a submodule? What about to add subgroup? What about this? That's worked. Right, so we still have no errors. And now, yeah, but I skipped a bunch of proofs. And this is now a sheaf. And now the idea is I shouldn't need to do this. So it should already have a module structure. So this, I'm hoping that this could be, we can get rid of this. Module structure : equals infer instance. He said optimistically. Yeah, hard luck. And then compatibility. Bits : equals sign. Yeah, life is never so easy, was it? So where is my module? No, I never made it into a module. That's the issue. So can I turn a submodule into a module? That's the question. Can I make this into a module? Module. So this is module sheaf. In type obj. This is module for what ring? What did I just prove? It was a module for this ring here. There, the structure pre-sheaf. I claim it's a module for this, and the proof is two module. Is that a thing? Is that not a thing? How do I make a submodule into a module? What? Oh, what a bore. Is that really not a thing? Submodule. There's the definition of a submodule. And what I claim is submodule. To module, it is a thing. Submodule to module. Is it used? No, never. It's never used. So am I not in the right? What's the deal here? Where am I? I'm in namespace submodule underscore class. So it's submodule underscore class dot module apparently. So this is submodule underscore class dot to module. This object here. How about that? Do you love me lean? Yes, you do. Great. And so there's a pre-sheaf in ab, and there's a sheaf in ab, and oh man, what? No, come on. What? I tried so hard. We've made it. What was it called? We know its name. We know its name. Let's just give it its name. It's that. Module sheaf in type obj. What do you mean you've never heard of it? Is it m.module sheaf in type obj? And now let's compare that wants a u. There you go. Excellent. Can we golf it? Yes, we can. So I've skipped a bunch of proofs, and I haven't proved. So I've skipped a bunch of proofs which will be more of the same, and I haven't proved that. I haven't proved there's this compatibility, right? I haven't proved that everything is compatible with restrictions. But I have done some stuff. And so the question is, what do I do next week? Has anyone got any opinions? So I'm not going to do any more. But what shall I do next week? Okay, I will decide myself what I'll do next week. So next week I'll do more of the same. I'll perhaps finish the proofs which I've skipped this week. And then think of something else to do. I'll push this week's work out to the repository. Thank God for all that. Right, wonderful. Let's go home. Oh, I'm still recording.